Hello dear students, Michał Kalisiak here. Today will be less theory, more design work, because we'll do project clock. You're watching Introduction to Digital Systems. Let the tutorials begin. I would like to present you an object of our interest at this lab. This is a backpack clock projected and assembled by our friend Bartek Kola. Bartek, greetings to you.
Hi, my name is Bartłomiej Kola. I built that digital clock. Unfortunately, you can't see this spectacular construction for yourself. In my opinion, that circuit is one of the easiest to build usable digital circuits. I believe that the exercise prepared by Michał and Victor will be interesting and will replace hardware lesson well. Have fun and good luck!
So, what do we have here? Here is the heart of the clock. Quartz resonator with a resonant frequency of 32.768 kHz. The circuit of an oscillator here uses that quartz. And here we can find a circuit that makes 1 Hz square wave from 32.768 kHz wave. This 1 Hz signal goes to a decade counter. Decade means that it counts from 0 to 9. This is a counter of unity digit of seconds. The change from 9 to 0 triggers the next counter, which is responsible for tenth digit of seconds. And here is a circuit that detects digit 6, which allows us to make two things. First, to reset this counter immediately when 6 appears, so that we can see digits from 0 to 5, and the second function to trigger the next counter, so unity digit of minutes. For minutes it's the same story, so that counter counts from 0 to 9, and while resetting triggers the next counter here, which counts from 0 to 5 because it's reset immediately when 6 appears by this gate. And here are counters for hours. And the special thing is that hour should be reset when 24 appears. So here is a circuit that detects 24 and reset both digits, or should I say counters, of hours. Here are drivers for 7-segment LED displays. One driver per digit. Here are resistors to limit the current of each diode in the display. So there are 6 times 7 of them. Here is the circuit that adds 1 to minutes and hours. The on-off switches are used as triggers. Look how it works. Okay, so I press the switch of minutes. As you could see, oh, now it happened. Sometimes when pressing a switch, we have problems with multiple changes of state, which is due to debouncing of a switch. Oh, you can see here multiple changes of state during one press, but switch debounce and changes the state high and low multiple times. I'll show you how to reduce that effect in a couple of minutes. So look, these counters for minutes counts from 0 to 59, and counters from hours counts up to 23. Good. Now something very important in electronic devices. Here you can see the orange or brown ones. Those are ceramic capacitors. They are used in every connection of VCC, so plus 5 volts, for example here, connection of 5 volts to something. This capacitor reduces the noise on the power supply line. So one node of the capacitor is connected to plus 5 volts, as close to the chip as possible, and the second node of the capacitor is connected to the ground. Usually we use 100 nanofarads. You can find plenty of ceramic capacitors on the computer motherboard PCB, but smaller ones in SMD packages. Those, the blue ones, are electrolytic capacitors of bigger capacitance, but with the same functionality to reduce noises on the power line. They are not as critical as the ceramic ones. Okay, so I mentioned that we have sometimes problems with multiple changes of state when pressing the switch due to the bouncing of a switch. I'll use here a capacitor connected to pull-down resistor in parallel. So resistor is connected to switch and ground, and capacitor as well. This is electrolytic 22 microfarads capacitor, and look what is the result. So with capacitor, maybe there was one debounce, but I'm not pretty sure. And without, oh, there was. Okay, so with capacitor the problem is almost eliminated. Good.
Brilliant!
What is the subject of the project? Look here. This is clock without seconds, because minutes and seconds behave similar. Here is the clock that simulates the frequency of minutes. So it should be 1/60 Hz. However, this is default frequency. Never mind. In backpack clock, that would be signal from detector of 6 controlling 10th digit of seconds. Here in this subcircuit, I have a counter of unity digit of minutes that counts from 0 to 9. Here I have a detector of 10 to reset the counter inside and to trigger the next counter, and also here is 7-segment LED display driver to control this display. That subcircuit counts from 0 to 5, so inside we have detector of 6 to reset the counter inside and to trigger the next stage. Of course, another 7-segment LED driver inside as well. Here is the similar part to this, but not the same. Here is a counter of 10th digit of hours and a detector of value 24. So the detector takes something from this part and reset itself and the counter here. So that counter in this subcircuit is reset in 2 cases. First when 10 here arrives, and when here is 2 and here 4 arrives. Here we can set minutes. Oh, here when clock is high it doesn't work. Now it works. And hours. So let me show you. Too long. Let me show you here that it counts to 24. Well, that counts up to 9, and yeah. So here are just logic inputs. You should use push switch. You can find them here. Something like that. I think you should design the project in one file without subcircuits. It's not a very big circuit, however, up to you. I did subcircuits only to show you the circuit without showing the circuit. I will present you our main device the counter. Here we connect the clock. And here a driver for reset, just a logic input. I'll put here 7-segment LED display driver. And a display. Okay, we use in this project the stock driver. So it counts from 0 to F in hex, so from 0 to 15. Here we reset the counter with a high state. Now let's take a look at signals, the clock, and here Q0. I will combine it. Oh, reset, okay. Okay, so here you can see the clock, and here Q0, which is clock divided by 2. This signal is clock divided by 4, by 8, and so on. And very important thing, counter changes its state, so adds 1 on the rising edge of the clock. So here is signal of clock. At this moment counter adds 1 on the rising edge of the clock. Here on the falling edge nothing happens. Nothing happens, as you can see on bit Q0. And here on the next rising edge we have reaction. Counter changes its state. Very important thing. Let's assume that we want to have a sequence like that. It means that this counter has to reset immediately when 3 arrives, and both counters have to reset when here is 3 and here 2 arrives. We need only digits from 0 to 3, so 2-bit counter would be enough, but the minimal value here is 3, so we'll just won't use those 2 bits. Now let's prepare functions to design circuits to reset counters. Wait! You left the input floating. Oh, I'm sorry. I'm sorry, you're totally right. What a shame. Okay, so basically you cannot leave input of digital or analog circuit unconnected unless you really know what you are doing. For example, you know the construction of the input inside of a chip, and there's pull down or pull up resistor inside, or you've programmed your microcontroller so there's pull up or pull down resistor inside programmed. Okay, so we'll fix that inputs, connecting them to low state, so ground, and those as well. So now we can continue. To reset counter immediately when 3 arrives, we have to set high level on reset input of counter when 3 arrives. So the truth table looks like that. Here is most significant bit and least significant bit. We can prepare Carnot map, why not? So this function will be described by multiplication of both bits. To reset on 2, we set here high state, here don't care bit, because we do not expect the counter would be in that state. So Carnot map looks like that, and the function is just here, A. So most significant bit. So now we know that to reset this counter, we need to multiply those 2 bits. Good. Now, that signal would also trigger the next stage. So if we want to reset both counters immediately when 3, 2 arrives, that means that here we have to detect 3 and here to detect 2, which is just most significant bit. Here we detect 2, which is just most significant bit, so I'll just take it. And we multiply both signals. So this signal has to reset this counter and this counter. This counter resets in 2 cases, with this signal or this signal. So I'll just add them. Good. And to set manually this counter, we can just add here additional, let's say, clock. Done with switch by you, I'll use simple logic input. So let's take a look. Working. Good. And example with 4-bit number, most significant bit, least significant bit, detection of 7. So high state here, here don't care bits, Carnot map looks like that. That is the biggest loop, and function describing is B, C, D. So to sum up, your homework is to design a clock with minutes and hours, with functionality of setting both the minutes and hours, but not using just logic inputs, but with push switches. If you have any questions or doubts, please let us know. That is all for today. Thank you that we could meet together virtually. Take care and good luck.